Nothing is pulling you down. Nothing is holding you in that bed. Nothing is gripping your shoulders. Nothing is reaching up through the mattress. That is not a poetic way of putting it. It may be the literal state of affairs. Physics has measured gravity for 339 years and never once explained it. Newton wrote the equation, then said in print that he refused to guess at a cause. Einstein replaced the pull with curved geometry and never said what the geometry is made of. Now a small, stubborn group of theorists think nobody can explain gravity because there is nothing there to explain, that it is not a force at all, but the way an enormous quantity of information behaves as it settles into its likeliest shape, the way a rubber band pulls back with nothing pulling. By the end of tonight, you will know what they claim, what the evidence says, and where it falls apart. Before we begin, if this is the kind of question you like to fall asleep to, a quick like or subscribe really helps the channel grow. It means a great deal to me. Now, let's ease in. There is one force you have never once stopped feeling. Not for a second, not in your sleep, not before you were born. It is pressing you into whatever you are lying on right now, and it has been doing that continuously since the day you arrived, and it is the only force in physics that nobody has ever explained. I want to be careful with that word, because it is going to do a lot of work tonight. Physics has described gravity beautifully. It has measured it, modeled it, predicted its effects to more decimal places than almost anything else in science. What it has never done is say what the thing actually is. And once you notice that gap, you cannot stop noticing it. Start with how strange gravity is compared to everything else. There are 4 known interactions in nature. 3 of them behave in a family resemblance. The strong nuclear force binds the insides of atomic nuclei. The weak nuclear force governs certain kinds of radioactive decay. Electromagnetism runs light, chemistry, electricity, and the reason your hand does not pass through the table. All 3 have been written as quantum theories. All 3 have particles that carry them. All 3 have been tested to precision that borders on absurd. And then there is gravity, which does none of that. Consider how weak it actually is. Take 2 protons and put them near each other. They push apart electrically, and they pull together gravitationally, and the electrical push is stronger than the gravitational pull by a factor of about 10 to the 36th power. That is a 1 followed by 36 zeros. It is not a small difference. It is not even the same order of conversation. You can watch this yourself with a fridge magnet. Take a small magnet, a few grams of metal, and hold it above a paperclip on the counter. The paperclip jumps up. In that moment, a piece of metal you could lose in a pocket has just defeated the gravitational pull of an entire planet. 6 times 10 to the 24th kilograms of rock and iron under your feet, all of it pulling down, and it loses to a fridge magnet. Gravity is the force that shapes galaxies, and it cannot hold on to a paperclip. That weakness would be a curiosity on its own. What makes it a problem is that gravity has also refused, for about 100 years, to be turned into a quantum theory. Physicists have tried. The program is straightforward in principle. Take the classical field, quantize it the way electromagnetism was quantized, calculate. When you do that with gravity, the calculations produce infinities that cannot be absorbed or tidied away. Every other force submitted to this treatment. Gravity generated nonsense and kept generating it. So we have a force that is absurdly weak, that will not quantize, and that nobody can explain. Hold those 3 facts together, because by the end of tonight, you are going to see an argument that they are all the same fact, wearing 3 different costumes. Let me show you the size of the explanatory gap, because it is older and wider than most people realize. Isaac Newton published the law of universal gravitation in 1687, in the book we now call the Principia. Every mass attracts every other mass with a force proportional to the product of the masses and inversely proportional to the square of the distance between them. It is one of the most successful sentences ever written. It put people on the moon. Newton also knew perfectly well that he had not explained anything. He said so, in public, in print. In the General Scholium he added to the second edition in 1713, he wrote that he had not been able to discover the cause of gravity from the phenomena, and then he wrote the line that got quoted for the next 3 centuries: hypotheses, non fingo, I frame no hypotheses, I am not going to guess. In private, he was blunter. In a letter to Richard Bentley in 1693, Newton wrote that the idea of one body acting on another at a distance through empty space, with nothing in between to carry the action, was so great an absurdity that he believed no competent thinker could ever fall into it. He had written the equation. He thought the mechanism it implied was ridiculous. He published it anyway, because it worked, and left the explanation blank on purpose. 228 years later, Albert Einstein filled in that blank, or that is how the story is usually told. In November of 1915, Einstein completed the general theory of relativity, and the picture it gives is genuinely different from Newton's. There is no force reaching across empty space. Instead, mass and energy determine the shape of space-time, and objects moving freely simply follow the straightest available path through that shape. John Archibald Wheeler compressed it into a sentence that has been repeated ever since. Space-time tells matter how to move, and matter tells space-time how to curve. The predictive record of that theory is remarkable, and it is worth hearing laid out, because the thing I am about to say about it is not a criticism of its accuracy. It explained the anomalous drift in Mercury's orbit, 43 arcseconds per century, that Newtonian mechanics could not account for, and it did so with no adjustment, immediately. It predicted that starlight passing the edge of the sun would be deflected by 1.75 arcseconds, which Arthur Eddington's expeditions measured during the eclipse of 1919. It predicted that light climbing out of a gravitational field would be shifted toward the red, which Pound and Rebka confirmed in 1959 and 60 by measuring a frequency shift of about 2.5 parts in 1,000 million across 22.5 meters of a Harvard tower. It predicted that a binary pulsar would lose orbital energy to gravitational waves, and the Hulse-Taylor pulsar has been shedding orbital period in agreement with that prediction to better than 2 parts in 1,000 for decades. On the 14th of September, 2015, the 2 LIGO detectors caught a gravitational wave directly. In 2019, and again in 2022, the Event Horizon Telescope produced images of the shadows of 2 black holes, and both looked the way the equations said they should. Every one of those is a triumph, and not one of them tells you what space-time is. That is the whole point, and I want to put it as plainly as I can. General relativity says mass and energy curve space-time. It does not say what space-time is made of, or why energy should curve it, or what is doing the curving, or why the strength of the coupling is what it is. It is a description of behavior. A description is not an explanation. You can hear the difference if you compare it with a case where physics did explain something. Before the 1800s, we had thermodynamics. Gases have temperature and pressure and volume, and there are laws relating them. Those laws worked. Then Boltzmann and Maxwell and Gibbs showed what temperature actually is, the average kinetic energy of enormous numbers of molecules. And suddenly, the laws were not fundamental rules anymore. They were bookkeeping about something underneath. That is what an explanation looks like. Gravity has never had that moment. And there is a quiet embarrassment sitting underneath all of this that physicists do not talk about much outside the field. The gravitational constant, the number that sets how strong gravity is, the capital G in Newton's equation, is measured worse than any other fundamental constant in physics. The current internationally accepted value is about 6.6743 times 10 to the minus 11 in standard units. with a relative uncertainty of roughly 2 parts in 100,000. That sounds fine until you compare it. The fine structure constant, which sets the strength of electromagnetism, is known about 1,000 million times more precisely. Worse, careful experiments measuring G have disagreed with each other by considerably more than their own stated error bars for decades, and nobody has fully resolved why. The most fundamental thing we can say about gravity is a number we cannot pin down, attached to a mechanism we cannot describe. There is a technical name for the blank space. Physicists call it the problem of the microscopic degrees of freedom of spacetime. It is the question of what spacetime is composed of when you look closely enough, what the individual pieces are, the way a gas is composed of molecules. General relativity has no answer, because in general relativity, spacetime is not composed of anything. It is the stage. It is primitive. It just is. For most of the last century, the assumption was that we simply had not looked hard enough, and that a quantum theory of gravity would eventually reveal the pieces. But there is another possibility, and it has been gathering supporters quietly for about 30 years. What if the reason we cannot find the pieces of gravity is that gravity is not a thing that has pieces? What if gravity is not a force at all, not fundamental, not basic, not one of nature's ingredients, but something more like temperature, something that does not exist at the level of individual components, and only appears when you have an enormous number of them and you stop keeping track of each one? What if gravity is what a huge quantity of information looks like from far enough away? That is the question tonight, and I am going to answer it directly by the end. Not with a shrug, not with a maybe, but with the actual state of the evidence, including the parts that go badly for the idea. But we cannot get there yet, because the argument depends on a category of force that most people have never heard of, and it starts with something you can hold in your hand. Before anything else, I need to fix a word for you, because if you carry the usual version of it forward, the rest of tonight will sound like mysticism instead of physics. The word is entropy. You have almost certainly been told that entropy means disorder, that the universe tends toward mess, that things fall apart, that entropy is the reason your room gets untidy. It is a memorable image, and it is close to useless. Worse, it smuggles in a feeling that nature has a preference, that there is some force pushing things toward chaos, and that feeling is exactly wrong. Here is the actual definition, and it is a counting problem. Entropy measures how many different microscopic arrangements of a system would look identical from the outside. That is it. You look at a system and describe it in broad terms. This gas is at this pressure and this temperature. This deck of cards is shuffled. And then you ask how many distinct detailed configurations are consistent with that description. Low entropy means very few. High entropy means enormously many. Ludwig Boltzmann wrote it as a single line, S equals K log W, where W is the number of microscopic states compatible with what you observe. It is carved on his headstone in Vienna's Central Cemetery, which tells you something about how much it mattered to him. The K is Boltzmann's constant, which since the redefinition of the units in 2019 has an exact value of 1.380649 times 10 to the minus 23 joules per Kelvin. Take a deck of cards. There are 52 cards, so the number of possible orders is 52 factorial, which comes out to roughly 8, followed by 67 zeros. Of all those orderings, exactly 1 counts as perfectly sorted, suits in order, ace through king. Essentially all the rest count as shuffled. Now shuffle the deck. It will come out disordered. Not because the cards dislike order, not because there is a force pushing them toward mess, because sorted is one arrangement out of 8 followed by 67 zeros, and shuffled is nearly all of them. You did not push the deck toward chaos. You picked at random from a set in which order is almost impossibly rare. That reframes the second law of thermodynamics entirely. The second law says entropy tends to increase in an isolated system. Read the usual way, that sounds like a decree. The universe insists on decay. Read correctly, it is a census result. Systems move toward the descriptions that have more ways of being satisfied, because there are more ways of satisfying them. Nothing is being enforced. It is arithmetic with very large numbers. Josiah Willard Gibbs generalized this into the machinery that runs modern statistical mechanics. And in 1948, when Claude Shannon worked out the mathematics of information, he found a formula with the same shape. The story goes that John von Neumann told him to call it entropy, partly because the mathematics matched, and partly, von Neumann is supposed to have said, because nobody really knows what entropy is, so in an argument you will always have the advantage. It is a joke that has aged into something closer to a warning. Now that the word is fixed, I can show you the thing this whole video actually turns on. There is a category of force in physics that is not a force at all, in the way you are imagining. It is called an entropic force, and it is completely real. You can measure it with a spring scale, it will do work, it will lift things, and yet there is no fundamental interaction underneath it. It is bookkeeping that has learned to push. The standard example, and the one that matters most tonight, is a long-chain molecule floating in a warm liquid. Picture a sealed box held at a constant temperature. Inside, there is a single long molecule, flexible, free to bend anywhere along its length, with one end fixed to the wall. Nothing else is happening. Leave it alone, and it will curl up into a loose tangle. Ask yourself why. There is no coiling force. Nothing in the chemistry of the molecule prefers to be bent. It coils for the same reason the cards shuffle. There is exactly one way for the chain to be perfectly straight, and there are unimaginably many ways for it to be tangled, and the surrounding molecules are knocking it around at random. Random selection from that set produces a coil essentially every time. Now reach in and straighten it. You will feel resistance. You have to do work, and when you let go, it snaps back, not gently, but with a definite, measurable pull. That pull is a force. You could hang a weight from it, and there is no fundamental interaction producing it. What is producing it is the fact that straight configurations are rare, and coiled ones are common, and the thermal jostling of the surroundings keeps re-rolling the dice. Let me put you in the box for a moment. You are standing inside a sealed chamber, warm, still, holding one end of a molecule that runs away from your fingers into the middle of the space. It is long enough to see, thin enough that it drifts. The air around it, call it air, call it whatever the bath is made of, is invisible, and it is not still. Every molecule in that bath is moving, striking the chain from every direction at once, thousands of times a second, from above, below, left, right, no direction favored over any other. You draw the chain out straight. You can feel it now, an even tension against your fingertips, patient and continuous, like a thread of elastic. It wants to go back. That is what your hand is telling you. But nothing is pulling. Watch the bath again. The strikes are still perfectly random. Not one of those collisions is aimed at bringing the chain home. Each one nudges it into some new shape, and almost every new shape is more folded than the one before, simply because folded shapes outnumber straight ones by a margin with no name. Release your fingers, and the chain does not travel back along a line of force. It stumbles home through a crowd, and it arrives because almost every direction it could stumble is inward. Your fingers report a force. The physics reports a head count. Both are correct. The relationship is simple enough to state. Force times distance equals temperature times the change in entropy. F delta x equals T delta S. Rearranged, the force equals the temperature multiplied by the entropy gradient. Steeper gradient, stronger pull. colder bath, weaker pull, which is a strange sentence about a mechanical force, and a completely ordinary one about a statistical drift. You have one of these in a drawer somewhere. Rubber elasticity, the retractive pull of a stretched rubber band, is almost entirely entropic. The long polymer chains in the rubber coil, for the same reason the chain in the box coils. When you stretch a rubber band, you are not stretching bonds, you are unfolding tangles and lowering the entropy of a few billion chain molecules at once. This has consequences you can test in about 4 seconds. Stretch a rubber band quickly and press it against your upper lip. It is warm. Let it snap back and press it again. It has cooled. John Goff noticed that in 1805, and James Prescott Joule measured it properly in 1859, which is why it is called the Goff-Joule effect. And here is the strange one. Hang a weight from a rubber band, then heat the band with a hairdryer. It contracts. It lifts the weight. Almost every material in your house expands when you heat it. Rubber under load does the opposite, because heating it makes the thermal jostling more vigorous, which makes coiling more insistent, which pulls harder. That is not a material property. That is statistics operating a winch. The same category covers more than you would guess. The pressure of the air in this room is not caused by molecules pushing outward on purpose. It is caused by there being overwhelmingly more configurations in which they are spread through the room than configurations in which they are all gathered in one corner. Osmotic pressure works this way. So does the depletion force in colloids, which is strong enough to be used industrially. So does the hydrophobic effect. Oil and water separate, not because oil repels water, but because separating them frees up the water molecules to arrange their hydrogen bonds in far more ways. The force that folds proteins, and therefore the force that makes biology structurally possible, is a counting artifact. One more piece, and then I can pose the question this part exists to pose. In 1961, Rolf Landauer showed that information is not an abstraction that floats above physics. Erasing a single bit of information in a system at temperature T must release at least Boltzmann's constant times T times the natural logarithm of 2 as heat. It is a small amount. It is not zero. And in 2012, a team led by Antoine Beroux measured it directly and published the result in Nature. That result matters more than its size suggests, because it establishes something the rest of tonight depends on completely. Information is physical. Bits have thermodynamic weight. You cannot shuffle information around without paying for it in the same currency as heat. So here is where we stand. There are real, measurable forces in nature that no fundamental interaction is producing, forces that are purely the drift of a system toward the arrangements it has more ways of being in. Information is physical and carries entropy, and entropy produces forces, which raises an obvious and slightly uncomfortable question. If gravity belonged to that category, if the thing pinning you to your bed were an entropic force rather than a fundamental one, then there would have to be information somewhere for it to be the entropy of, not metaphorically, actually somewhere, stored, counted, in a place. So where, in an empty room, would you put it? The answer to that question came from a graduate student who was worried about a cup of tea. In the early 1970s, a young physicist named Jacob Bekenstein was working at Princeton under John Archibald Wheeler, the same Wheeler who coined the term black hole and who spent his career trying to reduce physics to geometry. Wheeler, by his own account, used to raise a small nagging problem with his students, and he raised it with Bekenstein. The problem was this. Suppose you have a hot cup of tea. Hot tea has entropy. A great many microscopic arrangements of water molecules would look identical from outside. Now take the cup to a black hole and pour it past the horizon. The tea is gone. It cannot be retrieved, it cannot be seen, it cannot affect anything outside ever again. and its entropy has gone with it. But the second law of thermodynamics says the total entropy of a closed system never decreases. Wheeler said that whenever he poured hot tea down a drain, he felt as though he were committing a crime. But at least in a drain, the entropy was still in the universe somewhere. Past a horizon it is not. Pour enough tea into a black hole, and you could quietly delete the second law of thermodynamics, one cup at a time. Bekenstein's answer, published in 1972 and expanded in 1973, was as bold as anything in 20th century physics, and at the time, almost nobody believed it. He said the entropy is not destroyed, because the black hole has entropy of its own, and when you throw something in, the black hole's entropy goes up by at least as much as you lost. Then he said something stranger. The black hole's entropy, he argued, is proportional to the area of its event horizon. Sit with how peculiar that is. The event horizon is not a thing. It is not a shell or a membrane. It is a location, the surface where the escape velocity reaches the speed of light, a mathematical boundary with nothing physical marking it. If you fell through one, you would notice nothing at all at the moment of crossing. And Bekenstein was proposing that this immaterial boundary is where the object's entropy is written, and that the amount of it is set by how big the boundary is. Stephen Hawking thought this was wrong, and he had a good reason. If a black hole has entropy, it must have a temperature. The two concepts are welded together in thermodynamics. And if it has a temperature, it must radiate, because anything with a temperature above absolute zero radiates. But the defining property of a black hole is that nothing gets out. A black hole that radiates is a contradiction in terms. Hawking was so unimpressed that in 1973 he co-wrote a paper with James Bardeen and Brandon Carter setting out 4 laws of black hole mechanics that looked exactly like the 4 laws of thermodynamics. And the explicit purpose of the paper was to argue that the resemblance was only a resemblance, a formal analogy, nothing more. Then he did the calculation properly, using quantum field theory in the curved space-time around a horizon, in order to demonstrate that Bekenstein was wrong. The calculation said Bekenstein was right. Hawking published in 1974, under the title Black Hole Explosions, in Nature, and followed it a year later with the full treatment. Black holes radiate. The radiation is thermal, it has a temperature, and it carries energy away, which means a black hole left alone will very slowly evaporate. In the process, Hawking's calculation fixed the constant that Bekenstein's argument had left open. The result is one of the very few equations in physics that unites gravity, quantum mechanics, and thermodynamics in a single line. The entropy of a black hole equals 1/4 of the area of its event horizon, measured in Planck areas. A Planck length is about 1.6 times 10 to the minus 35 meters, which is roughly 10 to the 20th times smaller than a proton. A Planck area is that squared, about 2.6 times 10 to the minus 70 square meters. So take a black hole's horizon, tile it in squares that small, count the squares, divide by 4, and you have its entropy, which means you have counted its microstates, which means, in the language of information, you have counted its bits. The temperature works out too. For a black hole with no spin, the Hawking temperature is inversely proportional to its mass. Bigger means colder, and astrophysical black holes are enormously cold. A black hole the mass of the Sun would sit at about 6/100ths of a millionth of a Kelvin, 60 billionths of a degree above absolute zero, which is colder than the cosmic microwave background by a factor of around 100 million. The supermassive black hole at the center of our galaxy is colder still, down around 10 to the minus 14 Kelvin. These objects are not evaporating on any timescale that matters. A solar mass black hole would take something like 10 to the 67 years. But the temperature is not zero, and that is the point. Now let me give you the number that started everything else. The entropy of a black hole with the mass of the Sun is roughly 10 to the 77th in natural units. The entropy of the actual Sun, a ball of plasma with something like 10 to the 57 particles in it, all moving independently, is around 10 to the 58th. So if you took the Sun and collapsed it, without adding anything, without changing its mass, its entropy would jump by 19 or 20 orders of magnitude. A black hole is the most information-dense object the universe permits. Nothing you can build packs more into a given region. And it achieves that by storing everything on a surface. It is worth pausing on how much resistance Bekenstein met, because the history is a useful corrective to the idea that physics accepts elegant arguments quickly. He was a graduate student proposing that the most extreme objects in general relativity obeyed the laws of steam engines. Senior figures told him he was confusing an analogy for a mechanism. The papers were published in journals well outside the center of the field. What eventually settled it was not persuasion, but calculation. Hawking's, done in an attempt to bury the idea. And the rule that emerged from it, once both halves were in place, is now called the generalized second law. The entropy of the matter outside a black hole, plus 1/4 of the horizon area, never decreases. Pour the tea in, and the horizon grows by exactly enough to cover the loss. The bookkeeping balances. It just balances on a surface rather than in a volume, and that is the detail that would not stay quiet. Which brings us to the part that broke the intuition of an entire field. Take any ordinary thermodynamic system, a gas in a box, a block of metal, a star. Its entropy is extensive, which means it scales with volume. Double the size of the box while keeping the density the same, and you double the entropy, because entropy counts arrangements, and the arrangements live in the space. This is not a subtle rule. It is one of the first things you learn about thermodynamics, and it holds for essentially everything. Black holes break it. Double the radius of a black hole, and the volume inside goes up by a factor of 8, because volume scales as the cube of the radius. But the entropy goes up by only a factor of 4, because area scales as the square. The information does not care about the space inside. It cares about the surface enclosing it. Read that again, slowly, because it is the hinge of the whole night. The maximum amount of information that can exist inside a region of space is not determined by how much space is in there. It is determined by the size of the boundary around it. That is not how anything is supposed to work. A library's capacity depends on the room, not the wallpaper. A hard drive's capacity depends on the platter, not the case. And yet the universe, at the one place where we can actually count its microstates, charges the bill to the surface. I am going to leave one thread deliberately loose here, because it has been walked through properly elsewhere, and it would take us off the road tonight. When a black hole evaporates, what happens to the information that fell in? Does it come back out, encoded in the radiation, or is it destroyed, which quantum mechanics says is impossible? That question is the black hole information paradox. Hawking spent 30 years on the wrong side of it, and he publicly conceded a bet about it in 2004. It matters here only as a marker of how seriously the area law is taken. Nobody disputes that a black hole has entropy and that the entropy sits on the horizon. The argument is entirely about what follows. What I want you to carry forward is smaller and stranger than the paradox. Somewhere in the machinery of the universe there is an accounting system, and it has a hard limit on how much can be true about any region. And when it enforces that limit, it does not measure the room, it measures the walls. Which raises the question Bekenstein and Hawking did not ask, and that somebody else did about 20 years later. Is that a peculiar fact about black holes? Or is it a fact about space? In 1993, Gerard Hooft asked whether the area rule was really about black holes at all, and answered that it probably was not. His argument runs on an ugly little thought experiment. Suppose you tried to violate the rule. Take a region of space, say a sphere, and start filling it with information, data, matter, whatever counts. Keep going past the point where a black hole of that size would have stored everything on its surface. What happens? Nothing exotic happens. You get a black hole, that much matter in that little space collapses, and the moment it does, its information content is precisely 1/4 of the horizon area in Planck units. You cannot exceed the surface limit, because the attempt to exceed it produces the object that enforces it. So the bound is not a quirk of black holes, it is a ceiling on space itself. Leonard Susskind formalized it 2 years later in a paper he called The World as a Hologram, and Raphael Bousso generalized it in 1999 into a version that works in curved and expanding spacetimes. The name that stuck is the holographic principle. Everything that can be true about a region of space can be encoded on the boundary of that region, on a surface with one fewer dimension. The word holographic is doing something specific there, and it is worth spending a moment on, because the popular version of it has drifted a long way from the physics. An optical hologram is a flat piece of film with an interference pattern recorded on it. The pattern looks like nothing, smears and rings. Shine the right light through it, and a 3-dimensional image appears, with real depth, which shifts as you move your head. The information for a 3-dimensional scene was fully contained in a 2-dimensional surface. No dimension was faked, and none was lost. It was encoded differently. That is the analogy being borrowed. It is not a claim that you are an image, or a projection, or a rendering. It is a claim about where the data can be written down without loss. Everything happening in a volume of space can, in principle, be described completely by degrees of freedom living on the surface around it, a description with one fewer dimension and exactly the same content. I want to make that concrete, because it is easy to nod at and hard to actually feel. Draw an imaginary sphere 1 meter in radius around yourself. Its surface area is about 12.5 square meters. Convert that into Planck areas and you get something like 5 times 10 to the 69th of them. So the absolute maximum information content of that sphere, everything about it, every particle, every position, every correlation, the total number of distinguishable things it could possibly be, is around 10 to the 69 bits. Not approximately, not typically, at most. There is no configuration of matter and energy that fits more into a sphere of that size, because any attempt collapses into a black hole, and the black hole caps out at exactly that number. Now notice where the number came from. It did not come from the volume of the sphere. It came from the skin. I want you to lie there for a moment and take that literally, because this is the anchor of the whole night, and it will make more sense on the second pass than the first. There is a boundary around the space you are occupying. Pick any surface you like, the walls of the room, an imaginary bubble at arm's length, the outline of your own skin. Everything inside it, including you, has a total information content. Your position, your temperature, the arrangement of every atom in your body, the state of every photon crossing the space, all of it. And that quantity has a ceiling. The ceiling is finite, it is calculable, and it is set by the area of the boundary and not by the space it encloses. Which means, in a strict and technical sense, that everything true about the inside of that room fits inside a number written on its walls. That is not a metaphor. It is a theorem with a name and a derivation, and it inverts something so basic that most people have never thought to question it, the assumption that inside is where things are. On this accounting, the interior is not the storage. The interior is what the storage describes. Applied to you specifically, the Bekenstein bound gives a human body a maximum information content of something like 10 to the 45 bits. Applied to the observable universe, the entropy budget is dominated overwhelmingly by supermassive black holes, around 10 to the 104 in natural units, against roughly 10 to the 88 for all the photons of the cosmic microwave background put together. The universe's ledger is kept almost entirely on horizons. Now, the honest part. Is there an actual working example of this? A case where somebody has written down both descriptions and shown they are the same physics? Yes, one. In 1997, Juan Maldacena found a correspondence between a gravitational theory in a particular kind of curved space and a quantum theory living on its boundary with no gravity in it at all. Two completely different-looking theories in different numbers of dimensions describing the same thing. It is one of the most productive results in modern theoretical physics. It also does not describe our universe. Maldacena's construction requires a space with negative curvature, a saddle-shaped cosmos that folds in on itself. Ours has a small positive curvature term instead. The expansion is accelerating, not contracting inward. Extending holography to a universe shaped like ours is an unsolved problem, and I want you to remember that it is unsolved, because in about 20 minutes it is going to become the exact hinge on which a very ambitious claim swings. There is one more ingredient to set down before we can put the pieces together, and it is the strangest of the three. In 1976, William Unruh showed that temperature is not an absolute property of empty space. Take a perfect vacuum. An observer floating freely in it measures nothing. No particles, no heat, absolute zero. Now take a second observer and accelerate them steadily through that same vacuum. That observer does not measure zero. They measure a warm bath of particles at a temperature proportional to their acceleration. Same vacuum. Two observers. One says it is empty and cold. The other says it is full and warm. Both are right, because in quantum field theory, the definition of a particle depends on the motion of whoever is asking. The temperature is small. Accelerate at 1g, the acceleration you are experiencing right now, sitting still on the surface of a planet. And the Unruh temperature works out to about 4 times 10 to the minus 20 Kelvin. That is why nobody has ever directly measured it. It would take an acceleration of around 10 to the 20th meters per second squared to warm the vacuum by a single degree. But the number is not zero, and the relationship is exact. Acceleration has a temperature. And the reason that matters here, rather than being a curiosity about accelerating observers, is what an accelerating observer sees behind them. If you accelerate steadily and never stop, there is a region of space-time whose light can never catch you. It falls permanently behind. That region has a boundary, a horizon, and it belongs to you and to nobody else, defined entirely by your motion. The warmth you measure is the warmth of that horizon, which means horizons and temperature are not exclusively a black hole phenomenon either. Accelerate hard enough in empty space, far from any mass, and you acquire a horizon with a temperature purely by moving. Now recall the equivalence principle, the observation Einstein called the happiest thought of his life. Standing on the ground is physically indistinguishable from accelerating in a rocket. If acceleration comes with a horizon and a temperature, and standing still in a gravitational field is the same as accelerating, then a gravitational field ought to come with a horizon and a temperature too. So here is the collection sitting in front of us. Information is physical and carries entropy. Entropy gradients produce real, measurable forces with nothing exerting them. The information content of any region of space is capped by its boundary, not its interior, and acceleration, the thing gravity produces, has a temperature attached to it. 4 facts, each one established independently by different people for different reasons, over about 25 years. Nobody set out to build anything with them. And then, on a Wednesday in January, somebody put them on the same page. The paper is 9 pages long. It uses no mathematics that a second-year physics student could not follow, and it was posted to a public preprint server on the 6th of January, 2010. Its author was Erik Verlinde, a theoretical physicist at the University of Amsterdam, already well known in his field for work in string theory and conformal field theory. There is a formula named after him that people in that corner of physics use routinely. He was not an outsider making noise. He was an established professional, making a claim that his own colleagues found either brilliant or embarrassing, and often could not decide which. The title was On the Origin of Gravity and the Laws of Newton. Here is what he did. Take a mass, a star, a planet, anything. Draw an imaginary sphere around it. The sphere is not a physical object. Nothing is there. It is a boundary you have chosen. Now apply the holographic principle and treat that surface as the place where the information about everything inside is stored. Call it a holographic screen. Now bring a small test mass in from outside, drifting toward the screen. Ask a single question. What happens to the entropy of that surface as the particle approaches? Verlinde's answer takes 4 ingredients, and every one of them was already in the literature. The first is the entropy change. Bekenstein had argued decades earlier that when a particle is lowered toward a horizon, the horizon's entropy increases by a fixed amount once the particle gets within roughly one of its own quantum wavelengths of the surface. Verlinde adopts this directly. When the test particle comes within 1 Compton wavelength of the screen's entropy increases by exactly 2 pi, in units of Boltzmann's constant. The Compton wavelength is Planck's constant divided by the particle's mass times the speed of light. For an electron, it is about 2.4 picometers. For a proton, about 1,000 times smaller. So the entropy gradient, how much the entropy changes per meter of approach, is fixed by the particle's mass and nothing else. The second ingredient is temperature. Unruh gave us that. Acceleration and temperature are locked together, with the temperature proportional to the acceleration. Verlinde reads the relation backwards. Instead of asking what temperature an accelerating observer measures, he asks what acceleration a given screen temperature corresponds to. The third ingredient is the bit count. The holographic principle says the number of bits on the screen is its area in Planck units, the surface area of a sphere, 4 pi r squared, divided by the Planck area. Larger sphere, more bits, and the count grows as the square of the radius. The fourth is the equipartition theorem, which is 19th century thermodynamics, and says that the energy of a system in equilibrium distributes itself evenly across its available degrees of freedom. Apply it to the screen. The total energy is shared equally among all the bits, giving each bit half of Boltzmann's constant times the temperature. And what is the total energy? The mass inside, by Einstein's most famous equation. Now combine them. The entropic force law from the rubber band. Force equals temperature times entropy gradient. Substitute the entropy gradient from the first ingredient. Substitute the temperature, which equipartition ties to the enclosed mass, divided by the number of bits. Substitute the number of bits, which the holographic principle ties to the area of the sphere. And then the arithmetic does something that is either a coincidence of extraordinary size or a message. Planck's constant cancels. The speed of light cancels. Boltzmann's constant cancels. Every quantum and thermodynamic quantity in the derivation disappears, and what is left standing on the page is a force proportional to the two masses and inversely proportional to the square of the distance between them. Newton's law of universal gravitation. Not assumed. Not put in at the start and recovered at the end. Derived from a surface, a bit count, a temperature, and a census. Let me put you at that surface for a moment, because the mechanism deserves to be felt rather than followed. You are drifting in empty space, very slowly, toward a boundary that is not there. There is a star somewhere below you, far enough that you cannot see its disk. The sphere you are approaching is only a choice, a mathematical shell drawn at your distance from the star, and it has no thickness, no color, no substance. If you reach out, you will not touch it. But imagine you can see the accounting. The surface is tiled, edge to edge, in squares so small that a proton spread across one of them would be like a continent spread across a grain of sand. Each square holds exactly one bit, one yes or no about the world inside, and the entire surface is covered in them, 10 to the 60-something of them, a ledger with no gaps. You drift closer, nothing changes, closer, still nothing, and then you cross a distance smaller than the width of an atom, 1 Compton wavelength, the scale at which you stop being a point and start being a wave, and one entry in that ledger flips. A fact about you that used to be filed on the outside is now filed on the inside. The surface's entropy ticks up by exactly 2 pi. That is all that happens. One line item, moved, and that movement is the entire mechanism of your falling. There is no hand, there is no pull. There is a bookkeeping system that finds one arrangement overwhelmingly more probable than another, and you are being sorted into it. And if that is right, if that is really what is going on, then something has quietly changed about a sentence you have used your whole life. You have always said that things fall because something pulls them. On this picture, falling is not being pulled. Nothing reaches. Nothing grips. A system drifts toward the arrangement it has more ways of occupying, and from inside that drift, it feels exactly like weight. Hold on to that sentence. We will come back for it at the very end, when it will mean considerably more than it does now. There is one detail in the derivation worth lingering on, because it is the part that makes physicists uncomfortable in a way that pure skepticism does not cover. When you assemble the 4 ingredients, you are combining a quantum constant, a relativistic constant, and a thermodynamic constant, Planck's constant, the speed of light, Boltzmann's constant. 3 different branches of physics, 3 different reasons for those numbers to exist, and in the final line, all 3 vanish. What emerges is a purely classical law with none of them in it. That is not what usually happens when you mix formulas together. It is what happens when the formulas were describing the same thing all along. Verlinder's own summary of his paper is almost aggressively plain. Gravity, he wrote, is explained as an entropic force caused by changes in the information associated with the positions of material bodies. The reaction was immediate and loud. This was one of the most discussed preprints in theoretical physics that year. The New York Times ran a profile of Verlinder in July of 2010 under the headline, "A Scientist Takes on Gravity." Physicists who normally never speak to journalists were being asked for comment, and the field split, roughly, into 2 camps that still exist. One camp found the derivation suspiciously easy. Newton's law is not supposed to fall out of 4 lines of thermodynamics. When something that foundational appears from that little effort, the natural suspicion is that it was smuggled in. That suspicion sharpened quickly into a specific technical charge: circularity. The critics pointed out that the Unruh temperature and the Bekenstein entropy relation are both results derived in a context where gravity already exists. Bekenstein's entropy is the entropy of a black hole horizon, and black holes are gravitational objects. If gravity is baked into the ingredients, then getting gravity out of them is not a derivation, it is a round trip. Verlinder's answer is that the ingredients are cleaner than they look. Unruh's result requires only quantum field theory in flat spacetime and an observer who is accelerating, no gravity anywhere in the derivation. Bekenstein's entropy argument is thermodynamic in character, resting on the second law rather than on the Einstein equations. Whether that defense holds is still argued about 16 years later, in print, by people who are extremely good at this. The other camp noticed something the first camp was too irritated to sit with. If the derivation is circular, it is circular in a very particular way. It closes a loop between thermodynamics and gravity that has been quietly tightening since 1972, and it does so with the constants cancelling exactly. Coincidences of that shape are not usually nothing. I am not going to adjudicate that for you tonight. Partly because nobody can, and partly because the argument gets much more interesting when it stops being about elegance and starts being about telescopes. But before we get there, I have to tell you about the claim in that paper that almost nobody talks about, and that is considerably more radical than the one that made the newspapers. Because deriving the law of gravity was not the boldest thing Verlinde did on those 9 pages. In the same 9 pages, Verlinde also derived Newton's second law. That sentence goes past most people without landing, so let me slow it down. Newton's second law is force equals mass times acceleration. It is the law of inertia, the statement that objects resist being accelerated, and that the resistance is proportional to their mass. It is the first equation in most physics courses on Earth, and Verlinde's claim is that it too is entropic. Think about which of the two claims is more audacious. Gravity, at least, is a relationship between two objects. You can imagine it being mediated by something. But inertia is not a relationship with anything. Inertia is a property an object seems to have entirely on its own, sitting in empty space with nothing nearby. It is the thing you feel when a car brakes and your body continues forward. It is the reason a heavy door is harder to swing than a light one. It has never needed an explanation, because it has never looked like it required one. It is just what mass does. Verlinde says no. Verlinde says that when you accelerate an object, you change the information written on the screens that describe it, and the entropy cost of that change is what you feel as resistance. Inertia is not a property of the object. It is a property of the accounting around the object. If that sounds vaguely familiar, it should, because there is a name for the intuition, and it is 140 years old. Ernst Mach argued in the 1880s that the inertia of a body cannot be a property it possesses in isolation, that it must somehow be determined by the rest of the matter in the universe. Spin a bucket of water in an otherwise empty cosmos, and the surface should stay flat, because there is nothing for it to be spinning relative to. Einstein loved this idea, gave it its name, Mach's principle, and set out to build it into general relativity. He did not fully succeed. General relativity has traces of Mach's principle in it, frame dragging chief among them, but it does not implement the idea cleanly. You can write down solutions to Einstein's equations, describing a completely empty universe in which a test object still has inertia. Mach would have hated it. The entropic picture puts Mach's intuition back on the table in a different currency. Inertia is not intrinsic. It is what the universe's information ledger charges you for changing an object's state of motion. Verlinde does not stop there either. In the last part of the paper, he sketches a relativistic version of the argument, using a generalization of his holographic screens, and argues that the same machinery yields the full Einstein field equations rather than merely their Newtonian limit. That section is compressed, and it is the least developed part of the paper, but the claim is on the record. Now, this is the point where I need to be honest with you about lineage, because presenting Verlinde as a lone figure who thought of this in 2010 would be a nice story and a false one. In 1967, Andrei Sakharov, the Soviet physicist better known outside science for his human rights work, proposed something he called induced gravity. His suggestion was that the equations of general relativity are not fundamental at all, but arise as a side effect of quantum fields living in space-time. On that picture, gravity is a kind of elasticity of the vacuum. Space-time resists being bent for the same reason a solid resists being deformed, because bending it changes the energy of everything living inside it. Sakharov's paper was a few pages long, and it went largely unpursued for decades. Through the 1990s and 2000s, the Indian physicist Thanu Padmanabhan built an entire research program on the thermodynamic reading of gravity. His result, developed across many papers, is that the field equations of a broad class of gravity theories, not just Einstein's, but a whole family of them, can be rewritten as thermodynamic statements about horizons. That is not a coincidence you would expect from a fundamental force. It is what you expect from a description that was thermodynamic all along. And in 1995, Ted Jacobson published 4 pages that are, in my view, the single sharpest result in this entire area. He assumed that the relationship between heat, temperature, and entropy that Bekenstein and Hawking found for black hole horizons holds not only for black holes, but for every observer's local horizon, everywhere in space-time. From that assumption alone, Einstein's field equations follow, not as a fundamental law, but as an equation of state, the same category of statement as the relation between pressure, volume, and temperature in a gas. There is a full episode's worth of material in that derivation, and we have walked through it in detail before. So tonight, it stands as one sentence with a great deal of weight in it. General relativity may be to some deeper theory what the gas laws are to molecules. So Verlinde is not an outlier. He is the most exposed point of a line of thinking that includes Sakharov, Bekenstein, Hawking, Unruh, Jacobson, and Padmanabhan. He is also, by a distance, the most attacked, and I want to tell you where the attacks land hardest. The weakest link in the 2010 derivation is the equipartition step. Equipartition is a classical theorem about systems in thermal equilibrium. It says energy spreads evenly across degrees of freedom. Verlinde applies it to the bits on a holographic screen, which are not classical degrees of freedom in any established sense. Nobody knows what those bits are. Assuming they share energy evenly is a reasonable guess, and it is not more than a guess. Sabine Hossenfelder produced a covariant version of the argument in 2010 that repaired several of the loosest steps and made the whole thing considerably more respectable mathematically, while remaining, publicly and repeatedly, skeptical that the physical claim is true. That combination is worth noticing. In this field, people often improve arguments they do not believe, because making a claim precise is the fastest way to find out whether it is wrong. Let me end this part with the word that everything now depends on, because I have used it a dozen times and I have not yet defined it properly. Emergent. A property is emergent when it exists at one level of description and simply does not exist at the level below. Temperature is the cleanest example. A gas has a temperature. A single molecule does not. Not a low one, not a high one. The question is malformed. A molecule has a velocity and a kinetic energy, and temperature is a statistical summary of enormous numbers of those, which means it comes into existence only when you stop tracking individuals and start counting. Pressure is the same. Viscosity, sound, the wetness of water, the shape of a wave, all of them are real, measurable, and none of them exist for one particle. And notice that calling them emergent does not demote them. The temperature of a fever is not less real because it is statistical. A sound wave will still break a window. Emergent does not mean illusory. It means the property belongs to the crowd rather than to the members, and that you will never find it by examining a member more closely, no matter how good your microscope becomes. If gravity is emergent in that sense, then the question that has driven a century of theoretical physics, what is space-time made of at the smallest scale, what is the quantum of gravity, may be the same category of question as asking for the temperature of one molecule. It sounds completely reasonable. It has a grammatical shape that suggests an answer exists, and it refers to nothing. That would be an elegant escape from 100 years of failure. It would also be worth precisely nothing, scientifically, unless the idea could be made to say something that Newton and Einstein do not, something a telescope could go and check, which is exactly what happened next, and it took 6 more years. We are about halfway, and this is a good place to stop climbing for a few minutes and look back down at the path. Here is the argument so far, in 5 sentences. 1. Some real, measurable forces in nature are not produced by any fundamental interaction. They are produced purely by a system drifting toward the arrangements it has more ways of occupying, and a stretched rubber band is the example you can hold. 2. Information is physical. It carries entropy, erasing it costs measurable heat, and it obeys thermodynamics like anything else. 3. The amount of information that can exist inside any region of space is capped, not by the volume of the region, but by the area of the surface enclosing it, at 1 bit per 4 Planck areas. 4. Acceleration comes with a temperature, and with a horizon, and standing in a gravitational field is indistinguishable from accelerating. 5. Put those together, a surface carrying information, at a temperature, with an entropy that changes when matter moves near it, and the entropic force that results is Newton's law of gravitation, exactly, with every quantum and thermodynamic constant cancelling out of the final line. That is the case. And I want to be scrupulous about which parts of it are contested, because it is easy to hear a chain of reasoning and assume every link has the same strength. Links 1 and 2 are not contested by anyone. Entropic forces are textbook physics, and Landauer's principle has been measured in a laboratory. Link 3 is not seriously contested either. The Bekenstein-Hawking entropy is one of the most trusted results in theoretical physics, and the holographic bound that follows from it is accepted by essentially everyone who works on quantum gravity, whatever else they disagree about. Link 4 is standard quantum field theory. The Unruh effect has never been directly observed because the temperatures involved are absurdly small, but the derivation is solid, and nobody expects it to be wrong. Link 5 is where the argument stops being consensus and starts being a proposal. Verlinde's specific assembly of those pieces, the 2π entropy jump, the equipartition of energy across screen bits, the identification of that particular surface as the thing doing the accounting, is his, and it is where the criticism lives. So the honest summary at the midpoint is this. Gravity is deeply, structurally thermodynamic, and nobody disputes that. Whether gravity is thermodynamic, whether that is all it is the open question. Now let me restart the climb, because there is a problem with everything I have just said, and it is the problem that makes the rest of tonight worth your time. The argument so far is elegant. Elegance is not evidence. Verlinde derived Newton's law, but we already had Newton's law. Reproducing something we already knew is a consistency check, not a discovery. Any theory that failed to reproduce it would be dead on arrival, which means passing that test tells you almost nothing. For an idea like this, to be science, rather than philosophy, it has to stick its neck out. It has to say something that standard gravity does not say. At some place we can go and look. So think about where you would look. If gravity is a statistical, emergent thermodynamic phenomenon rather than a fundamental law, then it should not be exactly Newtonian everywhere, in the same way that the ideal gas law is not exactly right for real gases. Statistical descriptions have edges. They work superbly in the regime they were built for, and they fray somewhere. The gas laws are the model to keep in mind. The ideal gas law works beautifully across an enormous range of everyday conditions, and it is not exactly true anywhere. Cool a gas toward its condensation point, or squeeze it until the molecules are nearly touching, and the law visibly fails, because the assumptions underneath it, point particles, no interactions, perfect statistics, stop being good approximations. Johannes van der Waals won a Nobel Prize for writing down the corrections. Nobody regards those failures as embarrassing. They are how you find out that a law is a summary of something else. So if gravity is a summary, it has correction terms, and there is somewhere they become visible. Where would gravity fray? Not in the solar system. Down here, accelerations are enormous by cosmic standards. The sun pulls on the Earth hard enough to bend it around a 290 million kilometer circle every year. Any statistical correction to that would be lost in the 9th decimal place, and in fact, the orbits of the planets and the Moon have been used to place very tight limits on exactly these kinds of deviations. Nothing shows up there. Not near black holes either, where gravity is at its strongest and general relativity has just been photographed doing precisely what it was told to do. The place a statistical theory should fray is the opposite extreme, where the accelerations are so small that the description is barely holding on, where you have got very little mass, spread very thin, moving very slowly, a long way from anything. I want to give you a feel for how small is here, because the numbers involved are outside ordinary experience in a direction people rarely think about. The acceleration you are experiencing right now, lying still on the surface of the Earth, is about 9.8 meters per second squared. The acceleration the Sun exerts on the Earth is about 6/1000ths of that. The acceleration the Sun exerts on Neptune, out at the edge of the planetary system, is about 6/1,000,000ths of what you feel. Now go out to the far edge of a spiral galaxy, a star orbiting in the thin outer disk, 40,000 light-years from the center. The acceleration holding that star in its orbit is around 10 to the minus 10 meters per second squared. That is, 100,000 million times gentler than the pull holding you to your mattress. At that acceleration, an object starting from rest would take about 30 years to reach walking pace. That is the regime where a statistical description would run out of road. And it is not a regime you can build in a laboratory. There is no way to shield an experiment down to accelerations that small on Earth. The only place those conditions exist is out there, in the thin edges of galaxies. Which means the outskirts of galaxies. And here is the thing that should make the hair on your arms move, if you know any astronomy at all. The outskirts of galaxies are where astronomy has had a problem for 90 years. They are the exact place where the numbers stopped working in the 1930s and stopped working again more convincingly in the 1970s, and where they still do not work today. They are the reason 5/6 of the matter in the universe is currently believed to be invisible. If gravity were emergent, this is precisely where you would expect the cracks to show. And there is an enormous, unexplained, thoroughly documented crack sitting there, which physics has spent half a century filling with a substance that nobody has ever detected. That could be a coincidence. It could also be the most important clue in modern physics. Before we can tell which, you need to understand exactly how good the case for that invisible substance actually is, and it is much better than the people who dislike it usually admit. In 1933, a Swiss-American astronomer named Fritz Zwicky pointed a fairly ordinary piece of mathematics at the Coma cluster of galaxies and got an answer that should have stopped the field in its tracks. Zwicky was measuring how fast the galaxies in the cluster were moving relative to one another. There is a standard theorem, the virial theorem, that relates the average speeds of objects in a gravitationally bound system to the total mass holding them together. Fast motion needs a lot of mass. Slow motion needs less. The galaxies in Coma were moving far too fast. Not by 10%, by a factor that implied the cluster contained several hundred times more mass than everything visible in it put together. At those speeds, with only the visible matter present, the cluster should have flown apart long ago. Zwicky proposed that the cluster contained a large quantity of matter that emits no light. He called it Dunkel Materie, dark matter. The result was essentially ignored for 40 years. Some of that was Zwicky himself, who was brilliant and abrasive in roughly equal measure, and who liked to refer to colleagues he disliked as spherical bastards, on the grounds that they were bastards whichever way you looked at them. Some of it was that the measurement was hard, and the conclusion was outlandish. He also proposed, in 1937, that galaxy clusters could be used as gravitational lenses to weigh the universe. That idea was also ignored, and it is now standard practice. The result that could not be ignored came from a different kind of measurement, taken by Vera Rubin. Through the 1970s, Rubin and her colleague Kent Ford used a newly sensitive image tube spectrograph to measure the rotation of spiral galaxies, starting with Andromeda and working outward through dozens of others. The technique is straightforward in principle. Light from the side of the galaxy rotating toward you is shifted slightly blue. The side rotating away is shifted slightly red. Measure the shift at different distances from the center, and you have a rotation curve. Orbital speed as a function of radius. Newtonian gravity makes a clear prediction about what that curve should look like. Most of a spiral galaxy's visible mass is concentrated toward the middle, so once you are outside the bulk of the light, you are effectively orbiting a central mass, and orbital speeds should fall off, dropping as 1 over the square root of the distance, exactly the way the outer planets orbit more slowly than the inner ones. Neptune takes 165 years to go around. Mercury takes 88 days. The curves did not fall off. They went out from the center, rose, leveled, and then stayed flat, all the way to the last measurable point, far beyond where the visible starlight had faded to nothing. Stars in the outer reaches of these galaxies were orbiting just as fast as stars much closer in. By the 80 paper Rubin published with Ford and Norbert Thonard, covering 21 galaxies, the pattern was undeniable and universal. Either those galaxies contained a great deal of unseen mass arranged in extended halos, or something was wrong with gravity at those distances. Rubin herself was careful about which of those it was. She spent decades pointing out that the observation was solid and the interpretation was not settled, and she never received a Nobel Prize for a measurement that reshaped cosmology. She died in December of 2016, a few weeks, as it happens, after the paper we are about to come to was posted, and a few weeks after the first observational test of it appeared. She would have enjoyed that timing. The field chose the mass, and I want to be very clear that the choice was not lazy. There is a version of this story where dark matter is a fudge factor invented to save an equation, and that version is wrong. The evidence became far broader than rotation curves. Here is what has to be explained. The cosmic microwave background, the light released when the universe first became transparent, 380,000 years after the beginning, carries a pattern of temperature ripples whose relative sizes depend sensitively on what the universe was made of at the time. Those ripples are acoustic. They are sound waves in the early plasma. Ordinary matter, which interacts with light, gets pushed around by radiation pressure and cannot clump until the universe cools. Something that ignores light does not have that problem and can start clumping much earlier. The measured heights of the peaks in that pattern require both components in a specific ratio, and no adjustment of ordinary matter alone will reproduce them. There is a second, independent constraint from nuclear physics. The relative abundances of hydrogen, helium, and lithium produced in the first few minutes of the universe depend on how many protons and neutrons were present. Measure those abundances, and you get an upper limit on the total ordinary matter in the cosmos, and it is far less than the total gravitating mass. And there is a third, from structure. Galaxies exist. They had to form from small density variations, and there was not enough time for ordinary matter to do it alone, because it stayed smoothed out by radiation until recombination. Something that did not feel that pressure had to build the scaffolding first. Add it all up, and you get the concordance picture from the Planck satellite results. The universe is roughly 68% dark energy, 27% dark matter, and just under 5% ordinary matter. Of the matter alone, the stuff that clumps and gravitates and forms structures, about 5/6 is invisible. Now here is the part I want you to sit with, because it is the most quietly unsettling fact in modern cosmology. Every single piece of evidence for dark matter is gravitational. Not most of it, all of it. Rotation curves are gravitational. Cluster velocities are gravitational. Lensing is gravitational. The acoustic peaks in the microwave background are the imprint of gravitational clumping. Structure formation is gravitational. We have never touched dark matter, never seen it absorb or emit a photon, never caught it in a detector. Every claim about it is an inference from the behavior of gravity. And gravity is the one interaction in physics that has never been explained. So the largest single component of the matter in the universe, 5 out of every 6 kilograms of it, is known to us exclusively through readings taken with the least understood instrument we own. We are confident about the reading. We do not understand the instrument. If the instrument is being misread, then so is the inventory, and the misreading has been in every textbook for 50 years. That is not a fringe thought. It is the entire motivation for the field of modified gravity, and it is why physicists who have no time at all for Verlinde still take the general question seriously. It would be a much smaller worry if we had found the particle. We have not, and it is not for lack of trying. For 4 decades, teams have built increasingly extreme detectors in increasingly remote underground laboratories, vats of liquid xenon, cooled and shielded and buried under kilometers of rock to screen out cosmic rays, watching for the single faint flash of a dark matter particle glancing off a nucleus. Lux Zeppelin in South Dakota, Xenont under the Gran Sasso Mountain in Italy, Panda X in China. Each generation is many times more sensitive than the last. They have found nothing. The limits on how strongly a dark matter particle can interact with ordinary matter have been pushed down by orders of magnitude, closing off most of the parameter space that theorists once considered natural. And the searches are now approaching a hard floor called the neutrino fog, the point at which neutrinos from the sun and the atmosphere produce signals indistinguishable from the thing being looked for. Below that, the search gets very much harder. The Large Hadron Collider has found no supersymmetric particles and no missing energy signature that looks like dark matter production. Axion experiments continue and have not detected an axion. Meanwhile, cold dark matter has its own internal difficulties on small scales. Simulations predict more satellite galaxies than we observe, predict the densest satellites should be brighter than they are, and predict sharp density spikes at galaxy centers where observations often show gentle cause. Honesty requires the other side of that ledger too. There are a couple of galaxies, one catalogued as NGC 1052 DF2, and a companion, that appear to contain essentially no dark matter at all. Their stars move exactly as fast as their visible mass predicts, and no faster. That is awkward for any theory in which gravity itself is modified, because modified gravity applies everywhere and cannot be switched off in 2 galaxies. It is comfortable for particle dark matter, which can simply be absent from a place. So the standing is this. The evidence that something is wrong with our accounting is overwhelming, 90 years old, and comes from half a dozen independent directions. The evidence about what is wrong consists of one interpretation, held for good reasons, that has failed every direct test for 40 years. Into that gap, in November of 2016, Eric Verlinde dropped a number. There was a problem Verlinde had to solve before he could say anything about galaxies, and it is the same problem I flagged earlier and asked you to remember. Holography works as a piece of concrete mathematics in a universe with negative curvature. Maldaceno's correspondence lives in that kind of space. Ours is not that kind of space. Our universe has a small, positive cosmological constant. The expansion is accelerating, driven by whatever dark energy is, and instead of a boundary at infinity, we have a cosmological horizon, a surface beyond which light will never reach us, because space between here and there is being carried away faster than light can cross it. That horizon, like every horizon in this story, has an entropy and a temperature, and it is enormous. The entropy associated with the cosmological horizon of our universe is on the order of 10 to the 122nd, larger than every other entropy in the cosmos combined, by a wide margin. Verlinde's 2016 paper, called Emergent Gravity and the Dark Universe, is an attempt to redo the whole derivation in a universe shaped like the one we live in, and the technical move at the center of it is this. In a negatively curved space, the entanglement entropy of a region obeys a pure area law. It scales with the surface, exactly as we have been discussing, and when you run the entropic derivation, you recover ordinary gravity. But in a universe with dark energy, Verlinde argues, there is an additional contribution to the entanglement entropy that scales with volume rather than area. Dark energy fills space, and its entropy is distributed through space, not written on a boundary. Now consider what happens when you put a lump of ordinary matter into that. The matter takes up room. It displaces some of that volume entropy, pushes it aside, removes it from the accounting, and the medium responds. The word Verlinde uses for the response is elastic. Space, in this picture, is not an empty stage. It is more like a substance with a memory, carrying a strain when matter is embedded in it, and pushing back against the displacement. And the pushback shows up as an extra inward acceleration on top of ordinary Newtonian gravity, an additional pull that gets relatively more important the further out you go, because the volume of displaced medium grows faster than the surface accounting does. Which brings back a shape we have already seen, the rubber band that nothing is pulling, except that now it is not a strip of latex in a drawer, and not a chain molecule in a box. It is the entire universe, and the thing being stretched is the entropy of dark energy, and the thing feeling the pull is every star in the outer disk of every galaxy. Let me put you inside that picture for a moment, because it is the most physical way to hold it. Imagine that all of space, the space in this room, the space between the stars, everywhere, is filled with a substance you cannot see or feel, not a gas, something slower and stranger, a medium with a memory that remembers being pushed. Now lower a heavy object into it, a stone, a star, anything with mass. The medium has to go somewhere. It is displaced outward, thinned, pushed aside, and the region around the object is left carrying a strain, the substance holding a shape it does not want to hold, and very slowly, very patiently, trying to close. Nothing about the object attracts anything. The object is not doing anything. It is simply present, and its presence has moved something aside. But the strain is real, and it extends outward, and anything else sitting in that strained region is nudged, not by the stone, by the medium's attempt to relax around it. The further out you go, the more medium has been displaced in total, so the effect does not fade the way you would expect a pull from a single object to fade. It thins out more slowly, and it keeps mattering long after the object itself has become a speck of light. And here is what that picture is claiming, if you hold it steady. The medium is dark energy. The strain is what we measure, and the extra inward pull that astronomers have spent 90 years attributing to a halo of invisible particles is, on this account, not a substance at all. It is the universe trying to relax back into shape. Now, That is the story. Here is the number. Because the number is what makes it dangerous. Verlinde's framework produces an expression for how much apparent dark matter an observer should infer at a given distance from a given amount of ordinary matter. The apparent dark mass squared equals the speed of light times the Hubble constant divided by 6 times Newton's constant, all multiplied by the ordinary mass and the radius. Every quantity on the right-hand side of that expression is measured, the speed of light. The Hubble constant, which is the expansion rate of the universe. Newton's constant, the visible mass of the galaxy, which astronomers can weigh from its light. And the radius, which is where you are looking. There is nothing to adjust, no free parameters, no knob to turn if the answer comes out wrong. And notice the shape of it. It is the apparent dark mass squared that depends on the ordinary mass, which means the apparent dark matter grows as the square root of the visible matter and grows linearly with distance. That is a distinctive fingerprint. It is not the same fingerprint that a halo of particles leaves, and it is not quite the same one that Milgrom's modification leaves either. 3 theories, 3 different signatures, 1 sky to check them against. That is extremely unusual, and it is worth understanding why it matters. A dark matter halo model has parameters: how much dark matter, how it is distributed, how concentrated it is at the center. Given a rotation curve, you fit those parameters and you get a good match, because you were allowed to choose. Verlinde's expression does not get to choose. It produces one answer, and either the sky agrees or it does not. And there is a second thing the framework does, which almost nobody expected. In 1983, an Israeli physicist called Mordechai Milgrom proposed a different fix for the rotation curve problem. Instead of adding invisible matter, he suggested modifying Newton's second law at very small accelerations. Below a critical acceleration, which he called a naught, the relationship between force and acceleration changes shape, and flat rotation curves come out naturally. The theory is called MOND, modified Newtonian dynamics. MOND is remarkably good at predicting the rotation curves of individual galaxies, better than dark matter halos are, using only the visible matter as input. It is also, at bottom, an equation Milgrom wrote down because it worked. The critical acceleration is measured, not derived, about 1.2 times 10 to the minus 10 meters per second squared. For 40 years, people have noticed something odd about that number. It is very close to the speed of light multiplied by the Hubble constant, divided by about 6. There is no reason in Milgrom's theory why a fudge factor about galactic dynamics should be related to the expansion rate of the universe. It is a coincidence that has sat there, unexplained, since the 80s, and it has bothered people. Verlinde's derivation produces that scale rather than assuming it. The speed of light times the Hubble constant over 6 comes out to about 1.1 times 10 to the minus 10 meters per second squared. It is not fitted. It falls out of the fact that the entropy being displaced belongs to the dark energy that sets the expansion rate. That is the single most impressive thing about the 2016 paper, and I want to give it its full weight before I start dismantling it. Because now I have to be careful, and Verlinde is careful about this himself, which is to his credit. The 2016 result comes with restrictions that he states plainly in the paper. It applies to systems that are static, spherically symmetric, isolated, and sitting in a roughly de Sitter background. It is not a complete relativistic theory. You cannot run it backward to the early universe. It cannot compute how structure formed. It cannot fit the acoustic peaks in the cosmic microwave background, which is the single strongest piece of evidence for particle dark matter, because it has nothing to say about a universe that was hot, dense, and nothing like de Sitter. And it inherits a problem it did not create. The Hubble constant sits right in the middle of the prediction. and the Hubble constant is currently the subject of the sharpest disagreement in cosmology. Measurements based on the early universe give about 67 kilometers per second per megaparsec. Measurements based on nearby supernovae give about 73. Those two numbers disagree by about 5 standard deviations, and nobody knows why. A theory whose central prediction depends on that constant inherits the ambiguity. So this is not a finished theory. It is a formula with a restricted domain and a specific, unhedged, parameter-free claim about what telescopes should see in the outskirts of isolated galaxies. Which meant, for the first time in this entire story, somebody could simply go and look. They did it in 6 weeks. The first test appeared on the 9th of December, 2016, about 5 weeks after Verlinde's paper. It was led by Margot Brouwer, an astronomer at Leiden, and it used weak gravitational lensing. Here is how that works. Mass bends light. So the light from very distant galaxies, passing near a nearer galaxy on its way to us, gets slightly distorted. Each background galaxy stretched by a fraction of a percent in a direction that depends on where the foreground mass sits. Any individual distortion is far too small to see, because galaxies come in all shapes anyway. But average over enough of them, and the random shapes cancel, and the systematic distortion emerges. That distortion is a direct measurement of the total gravitational mass of the foreground galaxy, including any mass you cannot see, out to distances far beyond where its own starlight has faded. Brouwer's team used about 33,000 isolated central galaxies from the kilodegree survey, isolated being important, because Verlinde's formula only applies to systems without close neighbors. They sorted them into 4 bins by stellar mass, measured the average lensing profile in each bin, and compared it against 2 predictions, a standard dark matter halo model with free parameters, and Verlinde's expression with none. Both fitted the data well. Read that again, because the fairness matters. Verlinde's parameter-free prediction reproduced the observed lensing profiles about as well as a halo model that had been allowed to adjust itself. A theory published 5 weeks earlier, deriving gravity from information and dark energy, with nothing to tune, described the measured gravitational field around 33,000 real galaxies. Brouwer was careful in public about what that meant. It was a first step, she said, not a confirmation. There was a long way to go for both the theory and the tests before emergent gravity could be considered a solidly tested framework. She was right to hedge, because the next results went the other way. In February of 2017, Federico Lelli, Stacey McGaw, and James Schombert tested Verlinde's prediction against something called the radial acceleration relation. That relation is one of the more remarkable regularities in astronomy. Across 153 galaxies of wildly different sizes and types, the acceleration you actually measure at any point in a galaxy is a tight, single-valued function of the acceleration you would predict from the visible matter alone. Give me the stars and gas, and I can tell you the real gravitational field, with very little scatter, in any galaxy you like. Verlinde's framework, applied to disk galaxies, does not reproduce that relation cleanly. It predicts a distinctive hooked feature in the inner regions, a place where the curve bends back on itself, and the data show no such hook. The authors found the theory could only be reconciled with the observations if the conversion from starlight to stellar mass was pushed substantially below standard values across the board. That is exactly the kind of adjustment a parameter-free theory is not entitled to make. Their conclusion was blunt. Emergent gravity, as formulated, is inconsistent with the radial acceleration relation. Then the results started arriving from every direction at once. Crescenzo Tortora and colleagues tested it on early-type galaxies, ellipticals, the big round ones, in 2018. It worked reasonably well for the lower mass ones and failed for the most massive. Alberto Diaz Tejedor and colleagues tested it on dwarf spheroidal galaxies, the small faint satellites orbiting the Milky Way. These are the most dark matter-dominated objects known, with inferred mass-to-light ratios in the hundreds, which makes them the sharpest possible testbed. The result was mixed in an interesting way. Emergent gravity worked fairly well on the classical Milky Way dwarfs, and failed when confronted with a larger and more varied sample. And then the theory ran into clusters. In 2019, Andreas Tamosiunas, David Bacon, Kazuya Koyama, and Robert Nicol tested emergent gravity on the scale of galaxy clusters, objects 1,000 times more massive than a galaxy. They used the Coma cluster, the same object Zwicky had weighed in 1933, and a stack of 58 clusters spread across redshifts from 0.1 to 1.2, combining X-ray surface brightness measurements of the hot gas with weak lensing measurements of the total mass. Their numbers are worth having precisely. For Coma, emergent gravity and general relativity agreed reasonably well in the range from 250 to 700 kiloparsecs from the center. At around 1 megaparsec, emergent gravity predicted a total mass about twice what general relativity with dark matter predicted. And at 10 megaparsecs and beyond, it was in strong tension with the data. When they applied a standard statistical criterion for comparing models, one that penalizes theories for extra complexity and rewards them for fit, general relativity with cold dark matter was preferred in every dataset they tested. A second group, working on massive relaxed clusters with optical, X-ray and lensing measurements together, reached the same conclusion the same year. The simultaneous fits from emergent gravity were significantly worse. And sitting behind all of that is the case that nobody in this argument enjoys discussing, which is the bullet cluster. The bullet cluster is two galaxy clusters that collided roughly 150 million years ago from our point of view, at something like 4,700 kilometers per second. When clusters collide, three things happen to three different components. The galaxies themselves are mostly empty space, so they pass straight through each other, essentially untouched. The hot gas between them, which is the great majority of the ordinary matter, several times more massive than all the stars combined, does not pass through. It collides, shocks, heats, and gets left behind in the middle, glowing in X-rays. So after the collision, the ordinary matter is in the middle, and the galaxies are out at the edges. Now measure where the gravity is, using lensing. In 2006, Douglas Clow and colleagues did exactly that, and found that the gravitational mass is not where the ordinary matter is. The lensing peaks sit out with the galaxies, offset from the X-ray gas by a couple of hundred kiloparsecs. That is very hard for any theory in which gravity is sourced by visible matter, because it means the gravitational center is demonstrably somewhere the visible matter is not. It is exactly what you would expect if most of the mass were a collisionless substance that passed straight through along with the galaxies. And emergent gravity, in its 2016 form, cannot even be applied to it. The formula requires a static, spherically symmetric, isolated system. Two clusters smashing through each other at 4,700 kilometers per second is none of those things. There is a fair objection to be made about all of this testing, and defenders of the theory make it. Verlinde stated a restricted domain of validity, static, isolated, spherically symmetric, and several of the tests pushed the formula well outside it. Applying an equation where its author said it does not apply, and then reporting that it fails, is not quite a refutation. On the other hand, a theory that only survives inside a narrow fence is not much of a theory, and the fence is not something the theory earned. It is a limitation of how far the derivation has been developed. That is the real difficulty. In the decade since 2016, The observational literature has grown steadily, and the theoretical framework has not kept pace. There is still no full relativistic version that can be applied to a colliding cluster, or an expanding universe, or the early cosmos. That is a serious criticism, and it is not the same criticism as saying the idea is wrong. Plenty of correct ideas spent decades as fragments. But it does mean that when a test comes back negative, there is nowhere obvious to go and fix it, and when a test comes back positive, it is hard to say precisely what has been confirmed. So, if you had stopped following this story in about 2020, you would have concluded, reasonably, that emergent gravity had had one good week in December of 2016 and had been losing ever since. Which is why the most recent result is so awkward and so interesting. On the 5th of January 2026, 7 months ago, Young Sub Yoon, Sang-hyun Han, and Ho Song Hwang posted a paper comparing Mond and Verlinde's emergent gravity directly, using radial accelerations measured in 23 dwarf spheroidal galaxies. Same objects, same data, two rival frameworks, head-to-head. In 21 of the 23 galaxies, emergent gravity followed the observed trend within the galaxy more closely than Mond did. The individual statistical significances ranged from slightly negative, meaning Mond won that one, up to 3.4 standard deviations. Combined across the whole sample, they reported emergent gravity favored over Mond at 5.2 standard deviations. 5 sigma is the conventional threshold for a discovery claim in particle physics. This is not a discovery claim about gravity, and it should not be read as one. It is a comparison between two alternative frameworks on one class of object, not a test of either against dark matter. But it is the most recent significant result in this area. It used the sharpest available testbed, and it went the way almost nobody following the last decade would have predicted. So where does that leave the scoreboard? Emergent gravity works surprisingly well on isolated galaxies and on dwarf spheroidals. It fails on the inner structure of disk galaxies. It fails on galaxy clusters. It cannot be applied at all to the single most cited piece of evidence for dark matter, and it just beat its closest rival, decisively, on a sample of 23 small galaxies in January. A decade of the best data available to human beings, and the honest answer is still, sometimes. I want to say clearly what that pattern means, because there is a temptation to read it as a verdict, and it is not one. A theory that succeeds at one scale and fails at another is almost never a fluke. It is usually one of two things. Either it has captured something real and is missing the machinery it needs for the harder cases, or its successes are riding on a coincidence, in this case, the acceleration scale, that any theory hitting that scale would also inherit. Both of those are live, neither is settled, and the argument was about to move somewhere much smaller than a galaxy. The sharpest attack on the idea that gravity is information does not come from a telescope at all. It comes from a polished mirror the size of a credit card, in a shielded room in the French Alps. To understand it, you need to know about a peculiar kind of particle called an ultra-cold neutron. A free neutron, on its own outside a nucleus, is unstable. It lasts about 880 seconds before decaying. That is nearly 15 minutes, which by the standards of unstable particles is an eternity, and it is long enough to do experiments with. If you cool neutrons down far enough, they slow to a few meters per second. Walking pace. At that speed, something strange becomes possible. They will bounce off a polished surface at any angle of approach, the way light bounces off a mirror, because their quantum wavelength has grown long enough that the surface looks perfectly smooth to them. You can store them. You can pour them into a container with no lid, and they will not escape upward, because gravity is now strong enough, relative to their motion, to hold them in. Which means you have made something remarkable, a quantum particle in a box, whose ceiling is nothing at all, and whose floor is a mirror, and whose walls are made of gravity. In 2002, a team led by Valery Nesvizhevsky at the Institut Laue-Langevin in Grenoble did the experiment. Come and stand in the room while it runs. There is a horizontal mirror, polished to an almost inconceivable flatness, lying in a vacuum chamber. Above it, at an adjustable height, there is an absorbing surface. Think of it as a rough ceiling that swallows any neutron that touches it. Between them is a gap you can set to whatever you like, from about 1/10 of a millimeter down to a few millionths of a meter. A beam of ultra-cold neutrons enters horizontally through the gap. Some of them make it across and are counted at the far end. Others bounce too high, touch the ceiling, and vanish. So the count rate at the detector tells you how many neutrons could fit through a gap of that height. Now the operator begins closing the gap. At a millimeter, everything passes. At 1/2 a millimeter, everything passes. At 1/10, still fine. The count rate falls smoothly and gently as the gap narrows, exactly the way it would for a beam of tiny balls. And then, somewhere below about 20 micrometers, 1/4 the width of a human hair, the smoothness stops. The count rate does not taper. It drops, holds, and drops again. It comes down in steps. Below about 13 micrometers, essentially nothing gets through at all, no matter how carefully the beam is prepared. There is a flaw, and it is not the mirror. What you are watching is gravity behaving like an atom. The neutrons cannot occupy any height they like. Confined between a mirror below and gravity above, their vertical motion is quantized, exactly the way an electron's energy in an atom is quantized. There is a lowest allowed state, and it has an energy of about 1.4 picoelectron volts, around 1/1,000,000th of an electron volt, roughly 1,000,000,000,000 times smaller than the energies of the transitions that make atoms glow. That state has a characteristic height of about 13.7 micrometers. The neutron can be in that state, or the next one up, or the one above that. It cannot be in between. There are rungs and no ladder. It is worth pausing on how small that energy is, because it explains why nobody did this experiment sooner. A picoelectron volt is 1/1,000,000th of a millionth of an electron volt. The transitions inside an atom that produce visible light run at a few electron volts. Chemical bonds sit in the same range. The thermal energy of a room temperature air molecule is about 1/40th of an electron volt, which is still roughly 20,000 million times larger than the neutron's ground state above that mirror. To see these levels at all, the neutrons have to be colder, quieter, and better shielded than almost anything else that has ever been measured, and the mirror has to be flat to within a whisper. This was not a difficult experiment in 1960. It was an impossible one. This experiment has been refined ever since. The granite spectrometer at the same institute was built specifically to resolve the transitions between those rungs precisely. A collaboration called Q-Bounce developed a technique they call gravity resonance spectroscopy, driving the neutron from one gravitational state to another by vibrating the mirror at exactly the right frequency and watching the transition happen. The same apparatus has since been used to place limits on hypothetical fifth forces and on certain models of dark energy. Now here is the attack. In 2010, Archil Kobakidze published a paper with a title that leaves little room for interpretation. Gravity is not an entropic force. He published a follow-up a year later called Once More, Gravity is not an entropic force, which tells you how the intervening discussion had gone. His argument is this: an entropic force is thermal by nature. It arises from a system in contact with a heat bath, drifting statistically among an enormous number of microscopic configurations. That is the whole mechanism. The rubber band pulls because random collisions keep re-rolling its shape. But random collisions destroy quantum coherence. That is not a subtle point. It is the central fact of decoherence, and it is why quantum computers have to be cooled to within a whisker of absolute zero and shielded from everything. A quantum system, in contact with a warm, noisy environment, stops behaving quantum mechanically very quickly. So, Kobayashi argued, if the gravitational potential that holds a neutron above the mirror is generated by a hot holographic screen full of thermally fluctuating bits, then that neutron is sitting in a heat bath. It should decohere. The delicate, long-lived, sharply quantized bound states we actually observe in Grenoble should not survive. But they do survive, and their measured energies match, precisely, the prediction you get from ordinary quantum mechanics, with a plain classical Newtonian potential, no thermal bath, no screen, no entropy. He reinforced the argument with a second experiment, older and even more direct. In 1975, Roberto Colella, Albert Overhauser, and Samuel Werner split a neutron beam, sent the two halves along paths at different heights in the Earth's gravitational field, and recombined them. The two halves interfered, and the interference fringes shifted exactly as much as the difference in gravitational potential said they should. That experiment shows a neutron's quantum phase being altered by gravity while remaining fully coherent. Gravity, in that experiment, is acting on a wave function without disturbing it, which is not what a thermal force does. The counter-arguments exist, and they are technical. Masoud Chaichian, Markku Oksanen, and Anka Turianu argued that Kobayashi's analysis misidentifies the relationship between the microstates on a holographic screen and the state of a particle living in the emergent space, that the screen bits are not a heat bath the neutron is immersed in, and that treating them that way generates a contradiction that is an artifact of the treatment rather than of the theory. Kobayashi replied that the criticism was invalid and that his conclusion stands. That exchange has never been cleanly resolved. It has simply been left, the way many arguments in theoretical physics are left, with both sides certain and neither side able to force the issue. I am not going to adjudicate it for you, and I want to be explicit about why, rather than just declining. It is not that the question is unanswerable in principle. It is that answering it requires knowing what the microscopic degrees of freedom on a holographic screen actually are, and whether they are in thermal contact with a particle in the bulk in any meaningful sense, and nobody knows what those degrees of freedom are. That is the same blank space we started with, showing up again at the bottom of a completely different argument. But I want you to notice what has just happened to the scale of this discussion. We began with a question about the whole universe, what gravity is, what space-time is made of, whether 5/6 of the matter in the cosmos exists, and it has come down to whether a neutron moving at walking pace above a polished mirror in a room in Grenoble is or is not sitting in a heat bath. That is what a real scientific argument looks like from the inside. It does not resolve in a lecture hall. It resolves, if it resolves at all, in a very quiet room, with somebody adjusting a slit by a few micrometers and counting. So where does all of this actually leave us? What would have to be true for gravity to be information, and what would have to be false? There are three serious pictures of what is going on underneath, and I am going to lay all three out, with their strengths and their failures, because you are entitled to disagree with where this lands, and you cannot do that properly if I only give you one. The first picture is the standard one. Gravity is geometric, exactly as Einstein described, all the way down. Space-time curves, objects follow geodesics, and the missing mass is a real particle that we have not yet caught. Its strengths are formidable and are usually understated by people who want the alternative to be true. It fits the acoustic peak structure of the cosmic microwave background. It fits the primordial abundances of the light elements. It explains the growth of structure across billions of years of cosmic history. It handles the bullet cluster naturally. It does all of this with a small number of parameters, and the same parameters work across scales, spanning a factor of 1,000 million. Its weaknesses are equally real. The central object of the theory has never been detected in 90 years of inference and 40 years of searching, and the parameter space that theorists once considered most natural has been almost entirely excluded. There are persistent difficulties at small scales, and it leaves gravity itself completely unexplained. The geometry is still just there, still not made of anything. The second picture is the one we have spent tonight on. Gravity is emergent, an entropic, statistical, information-theoretic phenomenon, and the missing mass is a misreading of a description that is fraying where accelerations get small. Its strengths: it derives Newton's law rather than assuming it. It offers a reason why gravity has resisted quantization for a century. It produces the Mond acceleration scale instead of fitting it, which no other framework does. It survived its first weak lensing test with no free parameters, and it beat its closest rival on dwarf spheroidals in January of this year. Its weaknesses are severe. There is no full relativistic formulation applicable to our universe. It is restricted to static, isolated, spherically symmetric systems. It fails the inner radial acceleration relation in disk galaxies. It fails on clusters. It cannot be applied to the bullet cluster at all. It says nothing about the early universe, structure formation, or the microwave background, which is where the strongest evidence for its rival lives. And it faces an unresolved objection from a mirror in Grenoble. The third picture takes a completely different route. Instead of deriving gravity from thermodynamics or leaving it geometric, it tries to quantize spacetime directly: loop quantum gravity, causal set theory, asymptotic safety. In this family, space is not smooth at the smallest scale. It is granular, built from discrete elements, with a minimum quantum of area on the order of the Planck area, and gravity emerges from the quantum dynamics of that structure. Its strength is that it is a genuine attempt at a complete quantum theory of gravity, rather than a modification of the classical one, and the mathematics is rigorous. Its weakness is that it makes almost no predictions testable with any technology we have or expect, and its recovery of ordinary general relativity at large scales is still argued about. And there is a possibility that cuts across all three, which is the one I find hardest to shake. If gravity really is emergent, then the entire program of quantizing it may be a category error, not a hard problem, but a malformed one. It would be like trying to write down a quantum theory of the ideal gas law. You cannot quantize the gas law. There is no quantum of pressure. What you can do is find the molecules, and once you have them, the gas law comes out on its own as a consequence, and the original question dissolves. On that reading, a century of failure to quantize gravity is not a failure. It is the strongest evidence we have that we have been asking the wrong question. And the correct question is not what the quantum of gravity is, but what the degrees of freedom are whose statistics produce it. Now let me give you the reason this idea will not go away, even after the mixed scoreboard we just walked through. It is not Verlinde. It is that completely independent lines of research, using different mathematics, motivated by different problems, keep arriving in the same place. Ted Jacobson got there in 1995 by assuming the thermodynamic relations hold on every local horizon, and watched Einstein's equations fall out as an equation of state. Shinsei Ryu and Tadashi Takayanagi got there in 2006 by showing that, in Maldasena's correspondence, the entanglement entropy of a region on the boundary equals the area of a particular surface in the interior. Entanglement and area, the same quantity in two languages. Mark van Ramsdonk got there in 2010 with a thought experiment of remarkable simplicity. Take a boundary theory describing a connected spacetime and gradually reduce the quantum entanglement between two halves of it. As you do, the corresponding interior geometry stretches, narrows, pinches, and finally separates into two disconnected pieces. Remove the entanglement, and space itself comes apart, which suggests that entanglement is not something that happens in space. It is what space is made of. Juan Maldacena and Leonard Susskind got there in 2013 with the conjecture that entangled particles are connected by microscopic wormholes, that quantum correlation and geometric connection are two descriptions of the same thing. Brian Swingle got there through tensor networks, showing that the geometry of an emergent space corresponds to the circuit structure of entanglement in a many-body quantum state. Thanu Padmanabhan got there by rewriting the field equations of an entire family of gravity theories as thermodynamic identities. And as recently as last year, Ginestra Bianconi derived a modified Einstein equation from a quantum relative entropy, a measure of the difference between two descriptions of the same thing. 7 roads, different starting points, different tools, different people, no coordination. All of them arriving at the claim that geometry is downstream of information. When independent methods keep converging on the same strange destination, that is usually a sign there is something there. It is not proof, but it is the kind of pattern that has preceded almost every major reorganization in the history of physics. And yet, I have to turn this back on itself, because it would be dishonest not to. I opened tonight by saying that a description is not an explanation, and I used it as an accusation against Newton and Einstein. Now watch it come back for the theory that promised to fix them. Suppose emergent gravity is right. Suppose gravity really is the statistical behavior of information on screens. Then what, exactly, are the bits? Nobody knows. Not Verlind, not Jacobson, not Van Ramsdonk. Every version of this picture can tell you what gravity is a description of, and none of them can tell you what the thing being described is actually made of. The blank space that Newton left in 1713 has not been filled. It has been moved one level down, and at that level it is exactly as blank as it ever was. Before I answer the question I opened with, let me clear away 3 things that circulate around this topic and are not true, because they get in the way. The first is that the holographic principle proves we live in a simulation. It does not. It is a bound on information density, a statement about how much can be true about a region. It says nothing about anyone running anything. There was even a direct experimental check on a related idea. A Fermilab instrument called the holometer was built specifically to look for a predicted jitter in space-time at the Planck scale, and in 2015 it reported finding no such signal at the level predicted. The second is that dark matter is a fudge factor invented to patch rotation curves. It is not. It is independently required by the microwave background, by nucleosynthesis, and by structure formation, and any rival has to reproduce all of that, not just the curves. The third is that physicists suppress alternatives. Verlinde, published in mainstream journals, was tested by independent groups within weeks, and those tests appeared in the leading astronomy journals in the world. It is a minority position, which is not the same thing as a censored one, and Verlinde has never claimed to have disproved Einstein. General relativity would remain exactly as correct as it is now. In the same way the gas laws did not become wrong when somebody found the molecules. So, we have the evidence, we have the objections, we have the honest scoreboard. It is time to answer the question. So, is gravity a force, or is it information? Here is the answer, and I am going to give it to you in 3 parts, in order of how confident anyone is entitled to be. The first part is not in dispute by anybody. Gravity is thermodynamic in character. That is established. Black holes have entropy, and it is proportional to the area of the horizon rather than the volume inside. They have a temperature, and they radiate. Acceleration comes with a temperature. Assume the thermodynamic relations hold on every local horizon, and Einstein's field equations follow as an equation of state. In the one place where holography has been made mathematically precise, entanglement entropy and geometric area turn out to be the same quantity written two ways. No serious physicist disputes any of that. Whatever gravity is, it is tangled up with heat, entropy, and information at a level far too fundamental to be an accident. The second part is disputed, and honestly so. The claim that gravity is nothing but information, that it is emergent, and that there is no fundamental gravitational interaction at all, is not established, and Verlinde's specific version of it is in real trouble in real places. It cannot handle clusters. It cannot handle the bullet cluster. It cannot do cosmology. It has an unresolved objection sitting on a mirror in Grenoble, and it has spent a decade without the theoretical development it would need to answer any of that. What it also has is a parameter-free prediction that survived its first weak lensing test on 33,000 galaxies, an explanation for an acceleration coincidence that has gone unexplained since the 1980s, and a result from 7 months ago in which it beat its nearest rival on 23 dwarf galaxies at over 5 standard deviations. That is not a theory that has won. It is also very clearly not a theory that has died. It is a live scientific question in 2026, and anybody who tells you it is settled in either direction is telling you about themselves rather than about the evidence. The third part is the one I find hardest to put down. Gravity has refused, for 100 years, to become a quantum theory. That refusal is usually treated as a technical obstacle, a hard problem awaiting a clever enough person. But there is exactly one class of thing in physics that behaves this way, and it is the class of emergent properties. You cannot quantize temperature. You cannot quantize pressure, not because they are difficult, but because they are not the kind of thing that has quanta. They are what enormous numbers of other things look like when you stop counting individually. If gravity belongs in that class, then a century of failure was never a failure of talent or of mathematics. It was a well-formed question asked about a badly formed object. There would be no graviton in the way we have been looking for one. Gravitons would be collective excitations, like sound waves in air, real, measurable, carrying energy, and made of nothing but the coordinated behavior of something else. And the right question would not be what the quantum of gravity is, but what the degrees of freedom are whose statistics produce it. That reframing does not prove anything, but it takes the single most stubborn embarrassment in modern physics and turns it into a clue, and clues that good are not common. It also explains something that has always been slightly odd about the search for a graviton. Nobody has ever proposed an experiment that could realistically detect a single one. The usual answer is that gravity is too weak. The other possible answer is that there is nothing there to detect. Now let me bring this back to where it started, and to you. Early on I told you that some forces are not forces. The rubber band that nothing is pulling, the chain molecule that snaps back, not because anything reaches for it, but because the coiled arrangements outnumber the straight ones so completely that random motion delivers it home every time. Your fingers report a force. The physics reports a head count. Both are correct. If the emergent picture is right, then that is not an analogy for gravity. It is a description of it. The medium is not latex. It is whatever the universe is keeping its accounts in. The strain is not in a polymer chain. It is in the entropy of space. And the pull is not on your fingertips. It is on you, right now. The pressure of the mattress against your back, the weight of the blanket, the particular heaviness of your arms that has been there so continuously since the day you were born that you have never once noticed it as a sensation, only as the way things are. If this idea is right, none of that is something reaching out and holding you. Nothing is pulling you down. Nothing ever has. There is simply an accounting underneath everything, and in that accounting, There are overwhelmingly more ways for the universe to be arranged, with you resting on the bed, than with you anywhere else. And so that is where you are. Not held, sorted. Falling is not being pulled. Falling is drifting toward probability. I do not know whether that is true, and I want to be straight with you about that, rather than end on a flourish. It might be the deepest thing anyone has said about gravity since 1915. It might be a beautiful wrong turn, an idea so elegant that it took a generation of very good people a very long time to work out that it does not describe this universe. Physics is full of both, and they are indistinguishable from the inside while the work is still going on. It is worth knowing that this will not stay unresolved forever, and that the instruments that will settle it are already switched on. The weak lensing measurement that gave emergent gravity its one clear win in 2016 used about 33,000 galaxies. The Vera Rubin Observatory in Chile, named, appropriately, for the woman who measured the rotation curves, began its 10-year survey of the southern sky and will map billions of galaxies, with lensing measurements far more precise than anything Brouwer had available. The Euclid Space Telescope is building a three-dimensional map of the distribution of matter across a third of the sky and most of cosmic history. Between them, over the next several years, they will produce lensing profiles for enormous numbers of isolated galaxies across a wide range of masses and environments. Verlinde's expression makes one prediction for those profiles, with nothing to adjust. Dark matter halos make another. Milgrom's modification makes a third. The signatures differ in shape, and the differences are not subtle once you have enough galaxies. This is a comparison the data will simply make, whether or not anyone likes the answer. And on the other side of the argument, the laboratory is closing in too. There are experiments now being designed to test whether gravity itself is quantum, whether two small masses, each placed in a quantum superposition of two positions, can become entangled with each other through nothing but their mutual gravitational attraction. If that entanglement is observed, gravity is carrying quantum information, and a purely thermal, statistical, decohering description of it is in serious trouble. If it is never observed, that silence starts to mean something too. Neither of those will happen tomorrow, but we are not talking about a question that will be argued about forever in seminar rooms. We are talking about a question with instruments pointed at it. But here is what does not depend on how it resolves. There is something underneath the equation you memorized in school. Newton knew it and said so. Einstein deepened the description without closing the gap. Bekenstein found that a black hole keeps its books on its surface. Hawking proved it while trying to disprove it. Jacobson found Einstein's equations hiding inside thermodynamics. Verlinde found Newton's law hiding inside a bit count. And every one of those results points the same direction, toward a layer of reality that is not made of particles or fields or even space, but of relationships, of how much can be known about a region, and how many ways there are for it to be what it is. We have not reached that layer. We have only found its shadow, cast upward, in the shape of a force. And the honest state of the art tonight is that when we ask what gravity is, whether it is a force or whether it is information, the answer is that nobody knows, and that the question is now being argued in units, against data, by people who could be proved wrong next year, which is, when you think about it, exactly what a good question is supposed to look like. Thank you for spending tonight with the one force nobody can explain. If this is how you like to fall asleep, a like or subscribe would mean a great deal. It helps me keep making these. And remember, the next time you feel your own weight settling into the bed, that may only be the universe finding its most probable shape. Good night, and may you never feel gravity quite the same way again.